All right, so get this. We're diving into AI that's not writing poems. It's tackling formal mathematical theorem proving.
Oh, that's right.
We're talking about logic that even like seasoned mathematicians find challenging. And we're
Yeah.
going to see how AI is like stepping up.
Yeah. It is a fascinating leap forward. We're not just asking AI to crunch numbers, we're asking it to engage in deep logical reasoning.
And to guide us, we've got a ton of material on DeepSeek-Prover-V 1.5, this new AI system that's making waves. So before we get lost in the AI jargon, let's just break down what formal theorem proving is and why we should care if a computer can do it.
Well, it's like building a logical skyscraper, brick by verifiable brick. Every single step needs to be absolutely airtight, following a strict set of rules. It's not about finding a solution, it's about proving that solution is undeniably correct.
Okay, so it's not just about the right answer, it's about showing the logic.
Exactly.
Why is this important for computers, though? It seems like a pretty niche area of math.
It might seem niche, but the implications are huge. Think about being able to verify the code for self-driving cars or aircraft control systems or the algorithms that manage financial markets. Being able to prove that those systems are correct could revolutionize safety and reliability.
Whoa, okay, so now it's getting really interesting. So where does DeepSeek-Prover-V 1.5 fit into all of this? What makes it different?
Well, DeepSeek-Prover-V 1.5 is a 7 billion parameter language model, but it's not designed to write poems. It's specifically trained for proving theorems in Lean 4, which is a programming language mathematicians use. What sets it apart is how it approaches proof generation. There are two main strategies: proof step generation and whole proof generation.
Okay, so let's unpack those two strategies. What's the difference and which one does DeepSeek-Prover-V 1.5 use?
Imagine you're building a house of cards. Proof step generation is like placing each card one at a time, meticulously checking for stability after every step. Whole proof generation is like constructing the entire house of cards in one go.
So proof step is slow and steady. Whole proof is risky but faster. Does
Yeah.
DeepSeek-Prover-V 1.5 pick one?
It actually uses a hybrid approach called truncate and resume. It starts by attempting whole proof generation, but if it hits an error during verification, it doesn't just give up.
Wait, so it's like building the whole house of cards, and then if it falls over, it examines the wreckage.
Yeah, exactly. It truncates the proof at the point of error, analyzes the feedback, and tries again.
So it's like an AI that learns from its mistakes. But how does it get better at this over time? Does it just keep building and collapsing houses of cards?
Well, it uses a process called reinforcement learning from proof assistant feedback, or RLPAF.
Okay, RLPAF. How does this feedback loop actually work? Does it get a gold star for a good proof?
The AI generates a proof, and the Lean 4 prover acts like a teacher. It provides feedback on whether the proof is correct or not. This feedback is used as a reward signal.
So it's like a game where the only way to score points is to create proofs that the Lean 4 prover accepts.
Exactly. And it's worth noting that this feedback is binary. The proof is either correct or incorrect. There's no partial credit.
That seems like it would make learning challenging.
It definitely presents unique challenges, but DeepSeek-Prover-V 1.5 has some innovative techniques to address this problem, which we'll get into later. But for now, let's focus on how it bridges the gap between human-like reasoning and the rigid logic of a computer program.
Right, because it's not like we can just have a conversation with a computer about abstract mathematical concepts. So how does it even begin to understand?
That's where chain of thought reasoning comes in. DeepSeek-Prover-V 1.5 is trained not just on Lean 4 code, but also on natural language comments that explain the reasoning behind each step in a proof. It's like having a mathematician whispering in the AI's ear.
Giving it a glimpse into the human thought process.
Yeah, exactly.
But even with those hints, keeping track of the logic in a complex proof must be incredibly difficult. How does it manage all of that information?
It uses something called tactic state information. Think of it as a snapshot of the prover's internal state at any point during the proof. It includes things like the current goals, the available hypotheses, and any previously applied tactics.
So it's like a roadmap.
Precisely. This tactic state information guides the AI's decision-making, ensuring each step builds logically upon the previous ones. But remember those innovative techniques we mentioned to address the sparse reward problem.
Hold on, before we jump into that, I need a minute. We've got formal theorem proving two approaches to proof generation DeepSeek-Prover-V 1.5 strategy. This whole chain of thought reasoning thing. My brain is doing backflips.
Yeah, it is a lot to take in, but that's the beauty of a deep dive. And trust me, the techniques they've developed to tackle that problem are really ingenious.
Okay, now you got me hooked. Let's dive into those techniques and see what kind of superpowers DeepSeek-Prover-V 1.5 has. All right, you were about to tell us about these superpowers DeepSeek-Prover-V 1.5 has for dealing with that sparse reward problem. How does it get so good at something where success is so hard to come by?
It all comes down to a clever algorithm called RMaxTS. It's a variation of something called Monte-Carlo tree search, or MCTS.
Ooh, chance and exploration. Sounds intriguing. Is
Oh.
this where the superpower comes in?
Exactly. Imagine you're trying to find the best move in chess. MCTS involves simulating many possible games from the current position, exploring different branches to see where they lead.
So the AI is playing out thousands of imaginary chess games.
Yeah, you got it. The AI explores different sequences, evaluates the outcomes, and then uses that information to determine the best path.
Okay, I can see how that would be useful in chess. But how does it apply to formal theorem proving?
Well, in this case, the game is trying to find a valid proof. The moves are the different tactics it can apply.
So instead of moving pieces, it's manipulating logical symbols, trying to create a chain of reasoning that leads to the conclusion.
Exactly. Now, here's where the superpower or intrinsic rewards comes in. Remember, the AI only gets a reward if it finds a complete and valid proof. Most paths it explores don't lead to a solution, so it doesn't get much feedback along the way.
Right, and that makes learning tough because it doesn't get much guidance. It's just trial and error with very few successes.
Exactly. So RMaxTS addresses this by giving the AI a small reward, an intrinsic reward, every time it discovers a new tactic state during its exploration.
It's like giving it a little pat on the back for being adventurous.
Precisely. This encourages broader exploration. But it's not just about wandering aimlessly. It also uses something called a discounted upper confidence bound, or DUCB, to guide its exploration.
Okay, another technical term. What's DUCB all about? Is it like a compass?
It's more like a decision-making system that helps balance exploration with exploitation. The AI needs to try new things, but it also needs to leverage what it already knows.
So it's like a treasure hunter who needs to balance searching for new areas with digging deeper in spots that have already shown promise.
That's a great analogy. DUCD is a formula that helps the AI decide which tactic to apply next based on a combination of factors: the potential reward, how often it's been tried, and how recently it's received feedback.
So it's considering its past experiences, potential rewards, and focusing on recent information.
Exactly. And this combination of intrinsic rewards and DUCB within the RMaxTS algorithm is a major reason why DeepSeek-Prover-V 1.5 is so effective. But the real test of any AI system is how it performs in the real world, right?
Absolutely. It's all well and good to have fancy algorithms, but can it actually solve real math problems?
That's where things get even more exciting. DeepSeek-Prover-V 1.5 was tested on two challenging benchmarks designed to push its limits: Mini F2F and ProofNet.
Okay, let's hear about these benchmarks. What kind of math problems, calculus differential equations?
Think of them as the SATs for formal theorem proving. Mini F2F is like the high school level exam. It's designed to test an AI's ability to solve problems that you might find in advanced high school math competitions.
So we're not talking about your everyday algebra problems. How did DeepSeek-Prover-V 1.5 fare against this tough crowd?
It did more than pass it impressed. Using the single-pass whole-proof generation approach, it achieved a pass rate of 60.2%. But when they unleashed the RMaxTS algorithm, the pass rate jumped to 63.5%.
Hold on, a 63.5% pass rate on a test designed for top-tier high school math whizzes. That's incredible.
Yeah, it is. To compare some previous top-performing models, we're only able to solve around 50% of the Mini F2F problems.
So DeepSeek-Prover-V 1.5 is setting a new standard.
Exactly. The researchers found that both the reinforcement learning aspect and the RMaxTS algorithm were crucial.
But high school math, even the advanced stuff, is still just one level. How does DeepSeek-Prover-V 1.5 handle more abstract university-level concepts? Can it compete with seasoned mathematicians?
That's where ProofNet comes in. This one is designed to test an AI's ability to prove theorems at the undergraduate level: real analysis, linear algebra, even topology.
Okay, now we're venturing into territory where I start to get a little lost.
Yeah.
These are the kinds of math courses that separate the true math enthusiasts from those who just want to get through their required credits.
Exactly. They require a deeper level of mathematical maturity.
So how did DeepSeek-Prover-V 1.5 do? Was it able to hold its own?
It actually surpassed expectations. On the ProofNet benchmark, it achieved a pass rate of 25.3% using the RMaxTS algorithm, which is significantly higher than previous models. Some of those models only achieve pass rates around 18%.
A 25% pass rate on a test designed for undergraduate math majors. That's still impressive considering the complexity.
It is. These aren't simple equation-solving exercises. We're talking about proving theorems that require creativity and logical deduction.
Right, it's like comparing a high school track star to an Olympic athlete.
Precisely. And to achieve these results, DeepSeek-Prover-V 1.5 leaned heavily on its ability to leverage the chain of thought reasoning.
So those natural language comments really helped the AI grasp these more nuanced concepts.
Exactly. Those comments acted as a bridge, allowing the AI to approach these problems in a more human-like way.
It's fascinating, but let's not forget that this is still a machine. What insights did the researchers gain into how DeepSeek-Prover-V 1.5 actually approaches these problems? What makes its thinking process unique?
One of the key takeaways was the importance of that balance between exploration and exploitation. Remember, the AI has to choose from a vast number of potential tactics, and it can't just try every single one randomly.
Right, it needs to be strategic. It's like navigating a maze.
Exactly. The researchers found that DeepSeek-Prover-V 1.5's success was heavily influenced by the intrinsic rewards and the DUCB mechanism.
So it's like the AI is constantly learning and adapting.
Precisely. That adaptive learning process is one of the things that makes DeepSeek-Prover-V 1.5 so powerful. But let's be realistic, even the most advanced AI systems have their limitations.
You're right. No system is perfect. What are some of the limitations they highlighted? What are the next frontiers?
One limitation is that while DeepSeek-Prover-V 1.5 excels at exploration, it could be even better at exploitation.
Wait, I thought we were talking about how it strikes a balance. What's the catch?
It's fantastic at exploring and learning, but it could be more strategic about pruning its search tree, about abandoning paths that are unlikely to work.
So it's like a detective who's really good at gathering clues, but maybe not so good at connecting the dots.
That's a great analogy, and this is where the concept of a critic model comes in.
All right, another new term. Give me the rundown on critic model. What is it, and how can it help DeepSeek-Prover-V 1.5 become even better? Okay, so a critic model sounds pretty important. What is it, and how would it help DeepSeek-Prover-V 1.5 get even better?
It's like a mentor guiding a student. It's an AI system trained to evaluate incomplete proofs, acting as an advisor. It helps assess the likelihood that a particular path will actually lead to a valid proof.
So it's like having a senior detective telling the rookie that clue's a red herring.
Exactly. A critic model could really help DeepSeek-Prover-V 1.5 prioritize the best options and avoid wasting time. It's about making smarter decisions.
That makes sense. But I imagine training a critic model is hard. Judging a complete proof is one thing, but evaluating an incomplete one and predicting its potential seems really complex.
It is a challenge, but it's one that AI researchers are working on. Developing a critic model could be a game changer.
Sounds like we're on the edge of something big. But before we get carried away with AI mathematicians taking over, what are the broader implications of this research? What does it mean for the future?
The potential is vast. Imagine using AI to verify the code for software in aircraft medical devices or financial markets.
That would be huge for safety. We could eliminate bugs before they cause harm. All right, so get this. We're diving into AI that's not writing poems. It's tackling formal mathematical theorem proving.
Yeah, that's right.
We're talking about logic that even like seasoned mathematicians find challenging, and we're going to see how AI is like stepping up.
Yeah, it is a fascinating leap forward. We're not just asking AI to crunch numbers, we're asking it to engage in deep logical reasoning.
And to guide us, we've got a ton of material on DeepSeek-Prover-V 1.5, this new
Oh, hey there, what's up?
Hey there, thanks for having me. Can we just wrap up the key points of this study?
Hey there, thanks for jumping in. I'm glad you're excited about this episode and ready to get into it.
Absolutely, we love having you chime in. So, to recap the points we've touched on so far, we've been looking at how AI is tackling formal theorem proving.
Yeah, it's a really interesting field. Not like your everyday AI. We're going from basic reasoning all the way to how these systems prove complex math.
Exactly. It's about deep logical thinking, not just number crunching. And we were just getting into why this is so important.
So, to pick up from where we were, it's not just about the right answer, it's about the logic. You might wonder, why is this important for computers? Seems kind of niche.
It might seem niche, but the implications are huge. Think about verifying code for self-driving cars or